In section 7.2 and 7.3, we're going to cover series solutions to ordinary differential equations. In series solutions, we're going to consider methods of solving second-order linear equations when the coefficients are functions of our independent variable. And remember that could sometimes be x or be t, depending on the text or the application. So it's sufficient to consider here the homogeneous equation where we have a function p of x times our second derivative, plus another function q of x times our first derivative, and a third function r of x times our y itself. And the sum of all of these terms is 0. And then since the procedure for the corresponding non-homogeneous equation is similar to homogeneous, we're going to focus solely on homogeneous to understand the process. A point x naught such that p of x naught is not equal to 0 is called an ordinary point. If p of x naught equals 0, then x naught is called a singular point. So if we had, for example, x, y double prime, then x equaling 0, so 0, if x were 0, that would be a singular point. All other real values for x would be an ordinary point. We can use power series to find a solution to our linear differential equations. Starting with y equals the sum from n equals 0 to infinity of a sub n times the quantity x minus x naught to the n. From there, when we take our derivative, it's pretty straightforward and exactly the way we would expect to take a derivative. When you have x to an n power and you take its derivative, our power rule says bring the n to the front and then take 1 away from n. So you would have n times x to the n minus 1. Well, here we have that again. The only difference now is that our x to the n involves other terms in here. We have our coefficient a sub n. So that would be something like if we had 2x to the third, where we would bring the 3 down to multiply by the 2 as the coefficient in the front of x. So we'd have 3 times 2, which is 6. And then we still have x. Now, instead of being to the third, it would be 3 minus 1, which is also 2. And in that case, now we have our n coming down to the front, and we have n minus 1 for the power. And if you'll notice, our coefficient is this a sub n. So what you learned about series in Calc 2 is going to carry in with how we're going to approach taking derivatives of a power series here in differential equations. So we brought down our power of n, we multiply it by a coefficient a sub n, and then our x minus x naught is now to the n minus 1. And the same process is true now when we take another derivative. Remember that n is a coefficient, a constant. And so now when we take down another derivative, there's no product rule needed because n is a constant. So n minus 1 is also a constant, and a sub n, in theory, is also a constant. It's the coefficient, and we will eventually find values of those once we get a little further into the process. So we can then bring down our n to the, or n minus 1 to the front as well. So now we have the n from before, and we have the n minus 1, and our a sub n. Those are all of our constants, if you will, times our x minus x naught, now to the power of n minus 2. And that's where we're going to stop with our series solutions in this case. There are certainly circumstances under which you could apply these to higher order, as you could most of the other material covered in this course, but we're going to focus only on second order. Let's take a minute to look at a few examples. Our first example says, find a series solution of the equation y double prime plus y equals 0. Now, if we did this using our constant coefficient solution, we could easily do this and say, if we let y equal e to the rx or e to the rt, here we would have e to the rx times r squared plus e to the rx equals 0. When we factor out our e to the rx, we're left with r squared plus 1. e to the rx is never going to equal 0. So we end up with r squared plus 1 equaling 0, which means r is plus or minus I. And if you remember from the section where we covered constant coefficients with complex solutions using our Euler equation, we have that y is c1 cosine x plus c2 sine x. So when we make our series solutions, we should still come up with a series solution that represents c1 cosine x plus c2 sine x. We may find out that we have a naught cosine x plus a1 sine x. So they're going to be a sub n's. But we should still come up with this same solution. So let's have a look at our radius of convergence here. So we talked about radius of convergence previously. And in this case, we have a radius of convergence for x that is infinite. So we get to choose the center of our series. So we are going to center our series, our power series, at x naught equals 0. 0 is not a point that will make our p of x 0, right? So that would be a singular point. So x naught here being 0 is not going to cause a singular point because the coefficient in front of y double prime is simply 1. There is no other real value for x that will ever cause that to be a singular point. So we'll choose our own center and we'll stick with x naught being 0. Because now when I do all of these derivatives with x and minus x naught is 0, so we just have x. So the nice thing is that simplifies things quite a bit. We can now say then that y is the sum from n equals 0 to infinity of a sub n, simply x now to the n. We then know that y prime would be the sum from n equals 1 to infinity of n a sub n x to the n minus 1. Because remember, when you take the derivative, you have to iterate your beginning index, your lower index on your solution. So we have then y double prime is now the sum from n equals 2 to infinity. We had to iterate one more time. We had the n before. We now bring down our n minus 1. We still have our a sub n, and now we have x to the n minus 2. And the other thing to remember here with these indices changing is here we started with n equals 0 will give us an x to the 0. For our first derivative, when we started n equals 1, that will start us out with an x to the 0. For our second derivative, when we begin with n equals 2, that also means our first term would be x to the 2 minus 2, which is still x to the 0. So there is a reason why we have to iterate our lower index every time we take a derivative. But now that we know what our function and its derivatives look like in terms of power series, let's plug it into our differential equation. So notice on this one, we don't need a y prime. We only need y double prime and a y. So let's take y double prime, which is the sum from n equals 2 to infinity of n times n minus 1, a sub n, x to the n minus 2. That's all y double prime. Let's add to it y, which is the sum from n equals 0 to infinity of a sub n x to the n, and that sum should be 0. Well, now we want to try to combine everything, but we have a problem because this x has a power of n minus 2, and this x has a power of n. Our goal is to get each part of our equation to be a series that has some coefficient or combination of coefficients times x to the n power. So if you remember back to our shifting index video, that means we're going to have to shift the first one from n minus 2 back up to n. And when we substitute an n plus 2 here for n, and we substitute it back in here for our lower index, That now drops our lower index back to 0. We'll change out each n to be n plus 2. So we'll have the sum from n equals 0 to infinity of n plus 2. And now we'll have n plus 2 minus 1, a sub n plus 2, x to the n plus 2 minus 2 is just n, which is exactly what we wanted. And then we'll add to it the sum from n equals 0 to infinity of a sub n x to the n, because that one already has x to the n power. The thing to remember here is that it's always important to get that x to the n power. It's not about where your index begins. It's about having that x to the n power so that you can now combine all of your coefficients. Because now that we have x to the n and x to the n, we can put all of the coefficients together and combine this into one singular summation. So I'm changing colors here on my pen. So if we add that up, then we have our sum from n equals 0 to infinity, because they both have the same lower index, of n plus 2, n plus 2 minus 1 is just n plus 1, a sub n plus 2, plus a sub n, all times x to the n, which equals 0. The next step is what's really important here, because you have to remember that the only way to make this statement true is if either the coefficients, that collection of coefficients is 0, or x to the n is 0. The only way x to the n is going to be 0 is if x itself is 0. But we already said it's not, because we centered our series around x not being 0. So we're going to say here, x to the n isn't going to be 0. What can be 0 then, and what must be 0 then, is our n plus 2 times n plus 1, a sub n plus 2 plus a sub n. And what we're going to do is we're going to solve for what we call a recurrence relation. We're going to solve for a sub n plus 2 in terms of a sub n. And then we're going to start n at our lower index there, which in this case is n equals 0. And we're going to find the first few terms and see if we can come up with a pattern. Okay, so let's relate a sub n plus 2 to a sub n. So if we subtract the a sub n to the other side, and then divide by the n plus 2 and n plus 1, we can find a sub n plus 2. So it would be 1 over, or negative 1, sorry, over n plus 2 times n plus 1, all times a sub n. And then we're simply going to start substituting in values for n. We're going to find the first few terms. This is called a recurrence relation. And I'm going to carry it over to the next page where we're going to start substituting in values of n. So we know that a sub n plus 2 is equal to negative 1 over n plus 2 times n plus 1. And now let's start plugging in values for n. And remember, our lower index on our sum started at n equals 0. So we also start at n equals 0. So let's find the n equals 0 term. Well, that would be a sub 0 plus 2 is equal to, oh, I forgot the a sub n up here. There we go. And it's equal to here then negative 1 over 0 plus 2 times 0 plus 1 a sub 0. Or a simpler way to write that would be a sub 2 equals negative 1 over 2 a sub 0. Now let's find n equals 1. For n equals 1, we have a sub 1 plus 2, and it equals negative 1 over 1 plus 2 times 1 plus 1 times a sub 1, which means really we have a sub 3 equals negative 1 over 3 times 2, which is 6. So negative 1 over 3 times 2, a sub 1, or negative 1 over 6, a sub 1. Now let's find this for n equals 2. We'll have, and now this time I'm not going to write out all the substitution of putting in 2 for n. This time we'll have a sub 2 plus 2 is 4 equals negative 1 over 2 plus 2 is 4 times 2 plus 1 is 3, a sub 2. And now remember, a sub 2 is negative 1/2 a naught. So we're going to go back here and even plug in a little bit further. So here we're going to say this is actually negative 1 over 12 times negative 1/2 a naught. Or we get a sub 4 equals a positive 1 over 24 a naught. Let's see what happens when we look at n equals 3. Well, then we would have a sub 3 plus 2, which is 5, equals negative 1 over 3 plus 2, which is 5, times 3 plus 1, which is 4, a sub 3. Well, again, we know what a sub 3 is. A sub 3 is a negative 1/6 a sub 1. So really, we get negative 1 over 20 times negative 1/6 a sub 1. Which means we get 1 over 6 times 2 is 12, so 120 a sub 1. And we're going to talk about what some of these values look like here in a moment. So we end up with a sub 5 is 1 over 120 a sub 1. If we continue on with this same pattern, when we look at n equals 4, we get a sub 6 is now negative 1 over 4 plus 2 is 6 times 4 plus 1 is 5, a sub 4. Well, again, a sub 4 is 1 over 24, a naught. So you get negative 1 over 30 times 1 over 24, a naught. Well, this is the same as negative 1 over 6 times 5 times 4 times 3 times 2 times 1 a naught, or a negative 1 over 6 factorial a naught, because 1 over 24 is 1 over 4 times 3 times our 2 times 1. So 4 times 3 times 2 times 1, a naught here. So really, a sub 4 is 1 over 4 factorial a naught. And if we go back to a sub 2, that's really negative 1 over 2 factorial a naught. And these factorials become handy because that is how series solutions of sines and cosines look. So this trend continues over here with our odd valued n. So when we have 3 times 2, that's the same as negative 1 over 3 times 2 times 1, a sub 1, or negative 1 over 3 factorial times a of 1. When we now bring in that 1 times 2 times 3 times the 4 times 5, now we end up with a sub 5 is 1 over 5 factorial a sub 1. And let's look and see what happens when we look at n equals 5. We get a sub 7 is negative 1 over 5 plus 2 is 7 times 5 plus 1 is 6, a sub 5, which we already said again, we can now pull from here. Well, that was 1 over 5 factorial. So that's negative 1 over 7 times 6 times 5 factorial, a1. Or a sub 7 is negative 1 over 7 factorial, a sub 1. So something really interesting happens when we have even values of n. So for even values of n, we find out, by the way, we will usually say that n equals 2k. We find out then that a sub n, which we can also call a sub 2k, is the same as negative 1 to the k times a naught over 2k factorial. And when we look at a closed form for our odd values of n, so for odd values of n, or n equal to 2k plus 1, then we find out that a sub n here, which is our a sub 2k plus 1, is now negative 1 to the k times a1 over 2k plus 1 factorial, or our odd number itself factorial. So we were able to find what we would call closed forms for each of these coefficients. And the cool thing is when we start then putting it all together, then it looks a little bit like this, where we say that y is equal to the sum from n equals 0 to infinity of a sub n x to the n, and we wrote out the first 6 terms. We did the 0, 1, 2, 3, 4, and 5 terms. So we did n equals 0, 1, 2, 3, 4, and 5, which is actually 6 terms, because 0 counted. We ended up finding out that we had a naught, that is our very first term of our series every time is a naught. Then we had a1x. And then we had an a sub 2. A sub 2 was defined as negative 1 over 2 factorial a naught. So negative 1 over 2 factorial times a naught x to the, now n is 2 here, so it's x to the 2. Why did we not have an x for a naught? Because that would be x to the 0, which is 1. For a sub 1, we had x to the 1. And now for a sub 2, minus 1 over 2 factorial a naught x to the 2. And then for a sub 3, we said minus 1 over 3 factorial a sub 1 x to the 3, because we're on n equals 3. And then now we're up to n equals 4. So we now have a sub 4 x to the 4. So we have plus 1 over 4 factorial a naught, x to the 4th. And then we have plus 1 over 5 factorial a sub 1 x to the 5th. Minus 1 over 6 factorial a naught x to the 6th. Minus 1 over 7 factorial a1 x to the 7th. And we could continue on and on and on in this series. But we also found closed solutions for our sums. We said these are also the same as the sum as n goes from 0 to infinity of a naught times -1 to the n. Let me fix this one. -1 to the n over 2n factorial x to the 2n. And then we'll add to that our sum from n equals 0 to infinity of a sub 1 times -1 to the n over our 2n plus 1 factorial x to the 2n plus 1 from our closed forms for x naught, or sorry, for a naught and for a1. So if we were to factor out, not really factor out, but move our constant to the front, as we can do with series, it's one of our properties of series, we can then say this is a naught times the sum from n equals 0 to infinity of -1 to the n over 2n factorial x to the 2n plus a sub 1 sum from n equals 0 to infinity of -1 to the n over 2n plus 1 factorial x to the 2n plus 1, we discover that now this sum represents cosine. This is our Taylor series expansion for cosine x. And this guy is our Taylor series expansion for sine x. So truly, we still get y equals a naught cosine x plus a1 sine x. So they may not be c like we had in the very beginning, but you end up with the same answer. Let's try another series problem now that has a coefficient that includes an x and see if we can get to our solution a little bit quicker and see what happens when we don't have a solution that involves sines or cosines or any of the other functions that we can have Taylor series expansions for. So in this case, we're looking at 1 plus x squared times y double prime minus 8x y prime plus 20y equals 0. I'm going to choose to center the series at 0 again, because if x naught is 0, 1 plus 0 squared is still 1. It does not make p of x equal to 0, so I'm going to choose x naught to be 0 again. So let's let x naught equal 0 and center our series around x naught equals 0. Now, once again, that means our series and their derivatives now only include x to the n and n x to the n minus 1 and n times n minus 1 times x to the n minus 2. That makes our lives a lot simpler. What does not make our lives simpler is that now we're going to have a 1 plus x squared times our second derivative and an 8x times our first derivative and then a 20 times our function. So we're going to have some extra numbers here that we didn't have before. And it'll be okay. We'll manage it. It will work out just fine. So here we would say we have 1 plus x squared times our sum from n equals 2 to infinity of n times n minus 1 a sub n x to the n minus 2. That's our second derivative, right? Minus 8x times the sum from n equals 1 to infinity of n a sub n x to the n minus 1, our first derivative, plus 20 times our function y, which is the sum from n equals 0 to infinity of a sub n x to the n. And the whole sum is 0. Now, before we can go shifting indices here, we have to remember that we have a 1 plus x squared times the first sum, and we have 8x times the second sum. So that's going to change things a little bit when we bring those x's into our summations. Because if we now take, I'll tell you what, let's color code this. Let's make this red here. 1 plus x squared there. And we'll do our 8x here and our 20 there so we can see them a little bit clearer. Now, if I do 1 times the sum from n equals 2 to infinity of n times n minus 1 a sub n x to the n minus 2. And now we'll add to it the x squared times the sum. And all I'm doing so far is just distributing the 1 plus x squared to our sum. And that's n equals 2 to infinity, n times n minus 1, e sub n, x to the n minus 2. And now we'll have minus 8x still. But what I'm going to say here is let's bring the 8x inside. So we're going to say minus the sum from n equals 1 to infinity of 8x times n, a sub n, x to the n minus 1. And then plus in the same way, n equals 0 to infinity of 20 a sub n, x to the n. Well, this is where things start to get a little bit more interesting because now we have an x to the 1 and an x to the n minus 1. So we're going to end up adding that x to the 1, the power of the 1 to the n minus 1. And so this sum actually is now the sum from n equals 1 to infinity of 8 n a sub n x to the n minus 1 and then plus 1 from this x. Our last term is going to remain the same, n equals 0 to infinity of 20 a sub n x to the n. And our first term, we can lose the 1. That's just going to be the sum from n equals 2 to infinity of n minus 1 a sub n x to the n minus 2. But now when we move the x squared inside on our second term, we're going to have an x squared. And I'm going to kind of skip ahead a little bit here. We're going to bring in the x squared. We'll have to add that 2 to the x to the n minus 2. So really, we'll still have our n minus 1, our a sub n, but now we'll have x to the n minus 2, and then we'll add the 2 from the x squared. And this is where things get very interesting because we're looking at a first term. Oops, I'm going to put it in blue. We're looking at a first term that is the sum from n equals 2 to infinity of n times n minus 1 a sub n x to the n minus 2, plus now the sum from n equals 2 to infinity of n times n minus 1 a sub n x to the n, minus the sum from n equals 1 to infinity of 8 n a sub n x to the, now n plus 1 and minus 1 is just n again. And then the sum from n equals 0 to infinity of our 20 a sub n x to the n. So we now have an x to the n, an x to the n, and an x to the n. They have 3 different beginning indices, lower indices. So we'll have to deal with that in a minute. But the other bigger issue right now is that we have this x to the n minus 2 still. So we are going to have to shift the first sum. So we'll have to do 2 up on the inside, 2 down on the outside by letting n equal n plus 2. So we end up with our sum from n equals 0 to infinity of n plus 2. N plus 2 minus 1 is n plus 1. A sub n plus 2, x to the n. So now we're okay there. And then we're still going to add to it all of our other sums. So now we've got the sum from n equals 2 to infinity of n minus 1, e sub n x to the n, minus the sum from n equals 1 to infinity of 8 n a sub n x to the n, and then the sum from n equals 0 to infinity of now our 20 a sub n x to the n. And so now that we have all of our x's having the same power, we need to find a way to combine all of our terms together, all of our coefficients, and factor them all out in front of the x to the n. Herein lies the problem. Our first summation starts at 0. Our last summation starts at 0. Okay, but the middle two start at 2 and 1 respectively. So you have to go with the one that has the highest lower index, which in this case is n equals 2. So we are going to need to pull out from the first term, the first summation, the n equals 0 and the n equals 1 terms. So when n is 0, we get 0 plus 2 times 0 plus 1, a sub 0 plus 2, x to the 0, plus our a sub 1 term now is going to be 1 plus 2 times 1 plus 1, a sub 1 plus 2, x to the 1. And then we have the rest of the sum from n equals 2 to infinity of n plus 2 times n plus 1, a sub n plus 2, x to the n. Our next sum is already beginning at n equals 2, so we're okay there. So that's just 2 to infinity of n minus 1, a sub n, x to the n. For the next one, we have to subtract the first term out of this sum, which would be the n equals 1 term. So we would have our 8 still, and when n is 1, we would have times 1, a sub 1, x to the 1. And then we can subtract off the rest of the sum here from now n equals 2 to infinity of our 8, a sub n, x to the n. And in the same fashion now, we're going to need to pull out the first two terms of the last sum because it starts at n equals 0. So we have to pull out the 0 term and the 1 term. So we're going to have to add to this now our 0 term, which would be 20, right? 20 times a naught x to the 0, and plus our 20, running out of space, I'm going to write it underneath, a sub 1, x to the 1, plus the rest of the sum, which would be our sum from now n equals 2 to infinity of 20 a sub n, x to the n. Let's get that all in there. A sub n, x to the n, and the whole thing still equals 0. You can see that these solutions take up a lot of space. So now, if we start looking at what we have taken out, we have a singular term here and here. We have another one here, and then we have again this one and this one. And then we're left with our sums, each of which start at n equals 2. So what we're going to do on the next page is we're going to start combining all of these. We're going to simplify some of those beginning terms and put the summations all together. So we end up with our 2 a sub 2, right, plus our 6 a sub 3x. And then we have minus our 8 a sub 1 x to the 1, and plus our 20 a naught x to the 0 is just x, right? And then plus our 20 a sub 1 x to the 1, right? And then what we're left with after that is our big sum of all of the other terms together. So I'm going to have to write this probably below here, or it's going to spill onto the next line. So we're going to say plus our sum now from n equals 2 to infinity, and let's put it all together. So we would have n plus 2 times n plus 1, a sub n plus 2, x, and we don't need the x there, that's going to go in the end. And then we'll add, that's from our first summation. From our second, we have n times n minus 1, a sub n. And then from our third, we will have minus 8 n a sub n. And from our fourth and last, we will say plus 20 a sub n. And we put it all times x to the n, and the whole thing then equals 0. Ooh, so that's a lot. So we have n plus 2 times n plus 1, a sub n plus 2, plus n times n minus 1, a sub n, minus 8n, a sub n, and plus 20, a sub n. So let's start combining some more like terms. We have, let's see here. In the beginning, we've got an A0 and an A2. We've got a couple of A1s. I think that we can, let's see here. We have a minus A1 x to the 1, and we have a plus 20 A1 x to the 1. So if we put 20 minus 8, that's just 12. So I'm going to put these in order. I'm just going to say this would be 20 A0, right? And then our A1s are, we have 12 of them. So plus 12 A1 x, and I'm going to lose to the 1. Let's see here, plus 2a sub 2 and plus 6a sub 3 x. And then we have our big sum. But what we have to remember then is that we're going to end up equating coefficients here. So let's see if we can simplify that big sum. So we'll say this is plus the sum from n equals 2 to infinity. And let's look at this. We've got 3 separate places we have a sub n, but not a sub n plus 2. So we're going to leave this as n plus 2 and n plus 1, a sub n plus 2. But now, let's put all those a sub n terms together. We'd have an n squared, right, minus an n. So let's see here. I'm just going to do it this way. Let's do n squared minus n, minus 8n, and plus 20. And see if we can't find a way to simplify some things. So let's see here. It still gives us n plus 2, n plus 1, a sub n plus 2, plus, let's see here. Oh, it's just n squared, right? Let's see here. N squared minus 9n plus 20. So that's really n, let's see here, n squared minus 9n plus 20, a sub n. And we can factor that. What multiplies to give us 20 and adds to give us negative 9 would be negative 5 and negative 4. So we're going to be able to factor this one step further. So we'll have n equals 2 to infinity. Here now of n plus 2, n plus 1, a sub n plus 2, plus n minus 4, n minus 5, a sub n, all times x to the n equaling 0. And we still have all of these coefficients over here that have already been removed. But what we notice here too is that some of them have an x. 2 of them have an x value and 2 of them don't. So let's maybe pair them up slightly differently. Let's do 20a0 plus 2a2. And then we'll have 12a1x plus 6a3x. And if we factor out that x, we have 20a0 plus 2a2 plus 12a1 plus 6a3 all times x. And this is where we start getting into equating coefficients once again, like we were doing with our constant coefficient second order. Because on the left-hand side, we have 20a naught plus 2a2, and it has to equal all of the constants we have on the right, which is just 0. So we find out that a naught is negative 1/10 a2. Or that's really not what we're going to look for because we don't do our solutions, as we saw in the last one, in terms of a2. We do them in terms of a naught and a1. So let's go back and solve instead for a sub 2. So we've got 2a sub 2 now equals our negative 20 a naught, which means a sub 2 is a negative 10 a naught, which honestly sounds even easier than a negative 1/10. We also then have to equate the x's on the left and on the right. Well, on the right we don't have any, so we have 12a1 plus 6a3 has to also equal 0, or 6a3 equals negative 12a1, and a3 then is negative 2a1. These already sound like much happier numbers. And in the same fashion as the last problem, we know that x to the n is never going to be 0. So we're going to look at n plus 2 times n plus 1, a sub n plus 2, plus n minus 4, n minus 5, a sub n, and that's going to equal 0. Or if we solve for a sub n plus 2, we really get a negative times n minus 5, I'm going to put them in order here, and n minus 4, over n plus 2, n plus 1, all times a sub n. And then we have to go about substituting in values of n. So our first value would end up being n equals 2. Why is it 2? Go back to where we began. Our sum starts at n equals 2. So our recurrence relation here is only good starting at n equals 2. We've already found ways to equate a sub 2 and a sub 3 back to a naught and a1. Let's hope that when we put in our 2, we get an a sub 4, and then we can go on from there. So let's try it. So when we plug in n equals 2, we get a sub 4 equaling a negative times 2 minus 5 is negative 3, 2 minus 4 is negative 2, over 2 plus 2 is 4, and 2 plus 1 is 3, and this will be a sub 2. So we get a sub 4 is equal to a negative 3 times negative 2 over 4 times 3. Or in this case, we get a negative 1/2 a sub 2. And remember, we just found out that a sub 2 is a negative 10 a naught. So it's negative 1/2 times our negative 10 a naught. Or a positive 5 a naught. If we do n equals 3, we get a sub 5 equals a negative times 3 minus 5 is negative 2. 3 minus 4 is negative 1. Over 3 plus 2, which is 5, times 3 plus 1, which is 4, a sub 3. Or a negative 1/10 a third, or a3. And a sub 3 was negative 2 a sub 1. So we get negative 1/10 times our negative 2 a sub 1. Or a positive 1/5 a sub 1. And something really interesting is going to happen next, because when we look at n equals 4, a sub 6 is going to be a negative times, well, 4 minus 5 is negative 1. 4 minus 4 is 0. over 4 plus 2 is 6, 4 plus 1 is 5, a sub 4. We get 0. Funny thing is, now n equals 5, the same thing's going to happen because we have an n minus 5 on the numerator. We're going to get a sub 7 is equal to a negative times 0 times 1 over 7 times 8, a sub 5, which is 0. And then remember now, at n equals 6, that's going to rely on n equals 4, or a sub 4, which is 0. So all other terms, now, since they depend on these two, they're all 0. Well, what happens then? How do I write my solution? Well, it turns out it's easier than you think. Because now we have a y that's equal to the sum from n equals 0 to infinity of a sub n x to the n, which is going to be our a naught plus a1 x to the 1 plus a2 x squared plus a3 x cubed plus on and on and on. Well, in our case, that means we have a naught plus a1x plus now a2. If you'll remember, that is our negative 10 a naught. So we have plus here a negative 10 a naught plus, times our x squared plus a3, which was our negative 2 a1 x cubed. And then we get into our recurrence relation, and a4 is 5a naught. So 5a naught x to the 4th. And then we had 1/5 a1 x to the 5th, right? And then all of the others were 0. So we end up with a naught plus a1x minus 10 a naught x squared minus 2 a1 x cubed plus 5 a naught x to the 4th plus 1/5 a1 x to the 5th. And that's it. Our solution doesn't go any further. All other terms are 0. So typically what we will do then is say therefore y is, and we'll factor out the a naught and the a1. So we'll say it's actually a naught times 1 minus 10x squared plus 5x to the 4th, and then plus our a1, and that one would be 1, minus 2x cubed, and plus 1/5 x to the 5th. And that's where we would leave our solution. With example problem 3, we're going to expand on other concepts that we looked at in example problems 1 and 2. So in example problems 1 and 2, we chose x naught to be 0. In this problem, however, in this example problem, we were given x naught. When we have an initial condition, the initial condition's value for x is our x naught. So here we have 0. Both of those together tell us that x naught equals 0, and our series is now centered around 0. And the biggest difference is that we're going to be able to solve for a naught and a1, and then of course that what will follow is being able to solve for all of the other coefficients for our terms. So we would solve this one in exactly the same way, but when we get down to our a naughts and a1s and our sums at the end, we'll be able to plug in a naught and a1 and find the other terms. So without any further ado, let's jump right in. So we have 2 plus 3x times the sum from n equals 2 to infinity of n times n minus 1 a sub n x to the n minus 2 minus x times the sum from n equals 1 to infinity of n a sub n x to the n minus 1 plus 2x times the sum from n equals 0 to infinity of a sub n x to the n, and the whole thing is equal to 0. Just like in example 2, we're going to have to distribute the 2 and the 3x to the first summation, and the x in the second, and the x now in the third as well. So when we start moving our terms around, we end up with a 2 times our sum from n equals 2 to infinity of n times n minus 1 a sub n x to the n minus 2, and then plus our 3x. And that'll be out here on the outside. Our 3x times our sum from, again, n equals 2 to infinity of n times n minus 1 a sub n x to the n minus 2. And we still have minus our x, and just like last time, we're going to go ahead and move it into our sum from n equals 1 to infinity of n a sub n x to the n minus 1. And when we now bring this term in, it'll be plus 1. And then plus, now this was where things are going to get interesting, because now we have this sum from n equals 0 to infinity of our 2x a sub n x to the n. And once we start combining those terms, now we'll have an x to the n plus 1 term. So that's going to definitely complicate where we were before. So if we shift our index on this first one, we would end up with our sum from n equals 0 to infinity of our 2. And then we would have n plus 2. N plus 2 minus 1 is going to give us our n plus 1, a sub n plus 2, and x to the n. And now when we add our 3x into our sum from n equals 2 to infinity, we'll have our 3, our n minus 1, a sub n, now x to the n minus 2, and then bring in that plus 1. And now our next sum is n equals 1 to infinity of n a sub n, and now that we brought in the x that was on the outside, we now have x to the n. And then our last one is going to be the sum from n equals 0 to infinity now of 2, and a sub n is still there, but now when we put those x's together, we'll have something we didn't have in any of the other ones. Now we have x to the n plus 1. We haven't had an n plus 1 just yet, so we're going to have a very interesting summation there, because we're going to have to change the index a little bit there. So our first one is ready to go. It is n equals 0, the sum from n equals 0 to infinity of 2, n plus 2, n plus 1, a sub n plus 2, x to the n. It's already at an x to the n. We may have to pull out some terms later, but for now, that one is okay. Our third summation, so the first one, already at x to the n. Our third, already at x to the n. So where we're going to run into problems is when we look at the second one, which is going to be x to the n minus 1. And this last one, the fourth one, is going to be x to the n plus 1. Both of those are also going to require an index shift. So we'll carry down the first sum from n equals 0 to infinity of 2, n plus 2, n plus 1, a sub n plus 2, x to the n. And now we're going to have to shift, because we now have a sum from n equals 2 to infinity of 3 n minus 1 a sub n x to the n minus 1. And we're okay on this one. N equals 1 to infinity n a sub n x to the n. And this last one, let's go ahead and do our shift there. We have an n plus 1, so that's going to have to shift down, which means that n is now n minus 1. So our sum now goes from n equals 1 to infinity of 2 a sub n minus 1 x to the n minus 1 plus 1. That's going to give us our n, and that's what we were going for. So we have one last shift to do. which is our second sum. So our first is still n equals 0 to infinity, 2, n plus 2, n plus 1, a sub n plus 2, x to the n. And now our second sum currently is n minus 1, so we should need to shift n up by 1. So now all of our n's are n plus 1, which means our new sum is going to be the sum from n equals 1 to infinity of 3n, not quite n, remember we shifted it. We shifted it from n to n plus 1, so 3 times n plus 1, and now n minus 1, when we shift it in and change the n to n plus 1, we'll get n plus 1 minus 1, which is just n. A sub n plus 1, x to the n plus 1 minus 1. Minus our sum from n equals 1 to infinity of n, a sub n, x to the n, plus our sum from n equals 1 to infinity of 2, a sub n minus 1, x to the n. We're almost there with all of our x to the n's. So it looks like now we've got our sum from n equals 0 to infinity of 2, n plus 2, n plus 1, a sub n plus 2, x to the n, plus our sum now from n equals 1 to infinity of 3, and I'm going to move the n to the front, so 3 times n plus 1, a sub n plus 1, x to the n, minus our sum from n equals 1 to infinity of n, a sub n, x to the n, plus our last sum from n equals 1 to infinity of 2, a sub n minus 1, x to the n. So we now have all of our x to the n's, and we can start combining. But remember, there's one last thing to check, which is the lower sum. We have an n equals 0, an n equals 1, an n equals 1, and an n equals 1. So we're going to have to pull out the first term from our first summation. So we let n equal 0, so it's 2 times 0 plus 2 times 0 plus 1, a sub 0 plus 2, x to the 0, plus the rest of the sum now from n equals 1 to infinity, and now we can factor out our x to the n. We have 2, n plus 2, n plus 1, a sub n plus 2, plus our 3n, n plus 1, a sub n plus 1, minus our n, a sub n, and plus our 2, a sub n minus 1, all times x to the n equaling 0. And we know that x to the n can't be 0, so we end up now looking at our closed form. So let's see what we've got. We have 2 times 2 times 1 is 2, a sub 2 here, and that one's going to equal 0. Oh, sorry, it's not 2, I can count. That is 4. Sorry about that. That's 4, a sub 2. And when we equate coefficients on the right-hand side, that's just equal to 0, so a sub 2 is 0. If you'll notice here, we have a sub n plus 2, n plus 1, and an n minus 1. So essentially, there's nothing we can combine. So we come up with our recurrence relation here. I'll go back to red for that one. Our recurrence relation is going to be a sub n plus 2 is going to be, let's see here, we'll do negative 3n times n plus 1, a sub n plus 1, plus n a sub n minus 2, a sub n minus 1, all over 2 n plus 2 and n plus 1. So it looks a little bit complicated, but we'll make it work. We'll substitute in a few values of n and see if we can come up with a solution here. So we again had our two values from the first one, which was that a sub 2 is 0, and we had our recurrence relation where a sub n plus 2 is equal to negative 3n times n plus 1 times a sub n plus 1 plus n a sub n and minus 2 a sub n minus 1, and it's all over 2 times n plus 2 and n plus 1. So let's start evaluating at different points here. So remember, our sum started at 1. It was a sum from n equals 1 to infinity, so let's start with n equals 1. Then we get a sub 3 equals negative 3 times 1 times 1 plus 1, which is 2, a sub 2, plus 1 times a sub 1, minus 2 times a sub 1 minus 1, which is 0, so 2a naught, over 2 times 1 plus 2 is 3, and 1 plus 1 is 2. So we end up really with, well, we get negative 6a2, which is 0, we'll get to that one, plus a sub 1 minus 2a naught, all over 4 times 3, which is 12. And here's the other best part, is now we can also bring in y of 0 equals negative 1. That tells us that a naught is negative 1. And y prime of 0 is equal to 2, and that gives us a1. So we now know a2, a1, and a naught. So let's plug them in. So I end up with negative 6 times a2 is 0, plus a1, which we said was negative 1, and minus 2 times a naught. And a naught, oops, I put in the wrong one. a1 is 2, and a naught is negative 1. There we go. I think we got it there. And it's all over 12. So really, we get 4 over 12, which is 1/3. So we now know that a sub 3 is 1/3. Now let's let n equal 2. That a sub 4 equals 2 times negative 3 gives us a negative 6 times 2 plus 1 is 3. A sub 3 plus, or 2 plus 1 is 3, plus 2a2 minus 2a1, all over 2 times, well, 2 plus 2 is 4 times 3. So we get negative 18a3 plus 2a2 minus 2a1, all over 24. And again, we know some of these values. We have negative 18 times a3, which just found was 1/3, plus 2a2, which is 0, minus 2a1, which is 2, all over 24. So we really get negative 6 minus 4, so it's negative 10 over 24, or negative 5 over 12. So we end up with a4 is negative 5 over 12. we let n equal 3, we get a sub 5, and we get negative 3 times 3 is negative 9, times 3 plus 1, which is 4, a sub 4, plus 3, a sub 3, minus 2, a sub 2, all over 2 times 5 times 4, or negative 36 times a4 was a negative 5/12, plus 3 times a3 was 1/3, minus 2 times a2, which was 0, over 40. 12 goes into 36 3 times. Negative 3 times negative 5 is 15. And then plus 3 times 3 is 1. And then minus 0 all over 40. So we get 16 over 40 or 2 over 5. So we could keep going, but I think we have enough to say then that our y equals a naught, which is negative 1, plus a1, 2, x to the 1, plus a3, 1/3. Oops, sorry, I forgot the 2. Well, 2 is 0. We know that. So we don't have an x squared term. So we do skip over then to a sub 3, which is 1/3 x cubed, minus 5/12 x to the 4th. A to the 5th is 2/5, so plus 2/5 x to the 5th. And here we have our answer. We just can't forget that there's plus more terms. And that's that. So don't forget that we have some homework problems for this section, including from section 7.2, number 1, and from section 7.3, numbers 1 and 19.